12-2. Oh, only got two more of these. 12-2, 12-3, I'm done. It's more, but all right. Inference for two-way tables. Inference for two-way tables. So, why are you not showing up? There you are. Well, I got to bragging about it. Okay. We talked Monday on the goodness of fit. We talked Monday on the goodness of fit test, right? Goodness of fit test. Y'all bear with me because this thing is not going very fast at all. The goodness of fit test. Class, focus, please. Goodness of fit test comes from one sample, one variable. That's what's going to be your big key on it being goodness of fit. One sample, one variable. Okay? One sample, one variable. All of yours from Monday were one sample, one variable. All of yours from Monday were one sample, one variable. Today, again, bear with us as we are having issues. We're going to talk about homogeneity first. Homogeneity first. It's going to come from two or more samples. Two or more samples or two or more assignments. That's what's going to be the key difference between GOF and homogeneity. Very few get these confused because of the way you'll see these in just a second. Okay? And then we're going to talk about independence. Independence. These two are so similar. It's the only difference between them really is going to be the ho and the ha in the name of them. It's going to come back to one sample, but it'll be two different variables. And so again, guys, it's hard to somewhat see the difference between two samples and two variables. So just you have to read those questions really carefully. That's the hardest thing is about chi-squared is to talk about which one of those three you're doing, okay? If you're unsure, you're better off just saying we're doing a chi-squared test rather than saying it wrong. If you're unsure, you're rather off just saying chi-squared test. If you know for a fact it's a GOF, then say it. If you know for a fact it's homogeneity, say it. If you know it's independent, say it. If you're not too sure if it's one of those two, you can say two-way table, okay? But we'll talk about that as we're going through these, okay? But that's the difference between these three tests, okay? Again, one of them, GOF that we did on Mondays, one sample, one variable, okay? Color of M&Ms. They used a lot about the percentage of what type of nuts were in the mixed nuts, okay? Conditions for all three of these are the same. You have to have randomness, you have to have the 10%, and you have to have all expected counts greater than 5. All expected counts are greater than 5. The formula is the same for all three. It's the observed minus the expected squared over the expected. It's the summation of those. So all three formulas are the same. All three conditions are exactly the same. Okay? So we're happy about that. Yay. Hypotheses are a little bit different, but they're just a little bit different in the fact of we just have to state it like we're supposed to. So let's talk about the homogeneity. And the homogeneity, the two or more distributions are the same. There's no difference. They're equal. All of these are going to be somewhat, we're assuming there's no difference. We're assuming they're the same. We're assuming they're equal. However you want to say that. Again, I get this from their question. I get it from their question. So we will look at what their question is in the context, and I'll pretty much write my ho and my ha on that. But this is what you need to understand. We assume that they're all the same. We assume that there's no difference. We assume that the mixed nuts will follow the 52-25, whatever ratio, okay? Make sure it follows the population, not the sample, not the sample. That's where some students will mess up on these. I didn't emphasize that with GOF also. GOF, make sure it references the population. So we don't give numbers here. You have to give proportions. You can't give numbers. That was one of your first questions on your homework, right? We assume that there's going to be this many and this many. No, that alludes to the sample. Okay, so make sure. And then the high is they're not. They're different. They're not the same. They're not equal. However you want to say that, but we always assume that they're the same, and then there is a difference, or they're not equal, or they're not the same. However you want to say that, that's the ha. So they're equal, they're the same, there's no difference, and then it's the opposite. There's never a greater than or less than or anything like that. It's just that, okay? Again, make sure it's in the context of the problem and make sure it alludes to the population, not the sample. Those are the two biggest things about this, okay? We'll hit several examples of these today just to make sure you kind of follow how I would do that, okay? I always get this from the question and the problem. We'll read along the question of the problem and we'll make my ho and my ha from that. We just have to assume this part of it. No difference, they're the same, they're equal, and that there are different, or that they're not the same, or that they're not equal. No difference, equal, the same, yada, yada, yada. Any pencil still going yellow? Okay. Click. Let's look at this one, okay? Does background music influence what customers buy? One experiment in a European restaurant compared 3 randomly assigned treatments. So we have 3 different treatments. So they're independent of each other. Therefore, we know we're dealing with homogeneity. They had no music whatsoever. They played French accordion music, and then they played Italian string music. So we got no music, we got French, and we got Italian. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and something else. State the null and the alternative hypotheses. Well, we have to assume there is no difference between, and now I'm going to go to the context of the question. What am I trying to show? There's no difference in what they recorded, who ordered French, Italian, and other entrees. So there's no difference between what customers ordered and the type of music. Something like that. There is no difference in the true, see how they mention the true distributions? We want to make sure we're not alluding to the sample of entrees ordered at this restaurant when no music was played, French accordion music, or Italian string music. There's no difference between those. Okay? And then well, you don't want to write the whole thing again, so that's where you'll use a lot of the quotes or the squiggle marks or whatever you want to, because the only thing that's going to change is there is a difference. And again, you don't want to waste your time writing the whole thing again. AP won't care that you write the whole thing again. So you might as well just say, exactly the same, except there is a difference. Or you'll just write your little quotes or your little squiggle marks or whatever you want to write to show me that it is the exact same thing, except we're just talking about there is a difference. There is no difference. We could say what? The French, or no music and French accordion music and Italian string music are the same when or the food ordered. I guess the food ordered are equal. Have to be careful again about how you're going to say it. Make sure we're not alluding to the sample. Yes, no, maybe. Y'all okay? Kind of see that? These are the these are the observed counts. These are the observed counts. So we can see that there were 30 entrees ordered. There were a total of 84 ordered with no music. There were a total of 75 ordered with French, and there were a total of 84 with Italian. Okay, and we can see the distribution. There were 99 French, there were 31 Italian, and then 113 other. Okay, all this is what we observed. These are my observed counts. Observed counts. Well, we want to talk about what should be expected. So this is one of the harder things for students to understand. This goes back to probability. Okay, so soak this in. Those are my observed counts. Well, we assume that there's no difference. We assume that there's no correlation between all this stuff, right? We assume that there's no difference. If we assume there's no difference, guys, all these ratios need to be the same. So whatever 99 over 243 is, better be the same as this over this. Better be the same as this over this. We're trying to prove like independence. If you guys can think back to probability. Remember, if all these ratios are the same, then each one of these are independent from each other. So this over this, this over this, this over this. Everything better be the same. So here's basically how you're going to get these expected counts. If this over this, don't write all this down. I'm showing you mathematically. It's not that hard to do. If this over this is the same as that over 84, it should be, right? I don't know if it is or not, but it should be. Then they're independent. Then they have no correlation. They're all different. Well, to get this value here, the expected counts, you're going to cross multiply and divide by 243. Well, cross multiply means you're just multiplying this 84 and the 99. So I'm going to multiply those two numbers together, and then I'm going to divide it by that. And whatever that number is what I should expect to be there. Well, I've got to do that, holy cow, 1, 2, 3, 4, 5, 6, 7, 8, 9 times to get all expected counts. But that's what we got to do. Now, your calculator will do it all in one step, but you need to know how you're getting that value. So if I wanted to know, this would be an easy question for multiple choice. Easy type question for multiple choice. I don't know if it's easy or not, but this is the type of question. What are the expected counts for Italian entree and French music? Okay, that's what, so they're asking for that one right there. They're asking for Italian entree and French music. So I want that expected counts. I want that expected counts. One is the observed. That's not enough. That's not greater than 5, but I don't care about my observed. I want my expected counts to be greater than 5. Remember, that's one of my conditions. Okay, one of my conditions is expected counts better be greater than 5. So we got to list all of them. We got to find them all anyway. But that's the one I want to find. So what you do is you go to the French total, 75, and you go to the Italian total, the 31. And you're going to multiply those two together. And then you're going to divide it by the table total, 243. That would be my expected counts right there. Hopefully that number is greater than 5. If it's not greater than 5, then I can't do all these because we don't fit the condition. So whichever cell I want, if I want that cell right there, expected counts, you go to the total, multiply those two together, always divide it by the table total. Because all these ratios should be the same, and mathematically that's how you do it. Cross multiply the two that you know, divide by the third. That will find what that expected counts is. Any questions about expected counts? To find expected counts, we start by assuming Ho is true. That's what we have to assume. Well, if we assume Ho is true, then there's no difference between any of this stuff. And if there's no difference between any of this stuff, then none of this should determine the other one. And so if none of this should determine the other one, all the ratios should be the same. Well, I don't look at this ratio first. I look at the total ratios. 84 over 243 better be close to the same as this over this. Better be the same as this over this over this. 75 better be the same. Every single ratio should be the same. Well, in order to get those, you take the row total, column total. Where those two meet, that's the expected counts. You divide it by the table total. Okay? If the specific type of music is playing has no effect on the entree orders, the proportion of French entrees ordered under that condition should be that. 99, da, da, da. So this is how you find those expected counts. This is not on your formula sheet. You need to know this. It's the row total multiplied by the column total. Which one's a column, which one's a row? Doesn't matter. You're finding the intersection between those. The intersection, right? That's back in probability, the intersection of those two. And you divide it by the table total. You divide it by the table total. Questions? Good? So, again, these are my observed counts. These are my observed counts. Those are the expected counts. Expected counts can be decimals. Expected counts can be decimals. We didn't talk about that with GOF, right? Observed counts will never be decimals. Observed counts will never be decimals. If by some chance you mess that up, and it's going to give you an error. Anytime you put the observed counts as decimals, it will give you errors, always. It will always give you errors. So observed counts will always be integers. Expected counts could be decimals. You found that out on Monday, I hope. Any question about the expected counts? They'll give you the observed. They won't give you the expected. You got to find those. You got to find those. As with chi-squared GOF, expected counts should not be rounded. Those don't get rounded. That's what we expect in the long run. So don't round those. Observed counts will always be a whole number. They will always be a whole number. Expected counts gives an average number. Degrees of freedom. Degrees of freedom for this is a little different. Okay? You take your rows, however many rows there are, not including the total. Not including the total. And you subtract 1. So basically, however many columns there are, or how many, this is rows, okay, how many rows there are, minus 1. You're going to multiply that was a little fast, I guess. Multiply it by the columns, minus 1. So however many columns there are, subtract 1. Again, don't include the totals. Don't include the totals. Subtract 1. Count how many rows there are, subtract 1. Multiply those two numbers together. That is the DF. That is the DF. So this particular one, don't count the totals. Don't count the totals. So there's 1, 2, 3, 2. 1, 2, 3. Whoops, sorry. 2. 2 times 2 is 4. So the DF is 4 for this particular example. Rows minus 1 times columns minus 1. Rows minus 1 times columns minus 1. So this particular one, don't include the totals. That's where some students will mess up. Don't include the totals. There's 1, 2, 3, so there's 2. There's 1, 2, 3, so there's 2. 2 times 2 is 4. Some students like to cover up the last row and the last column and count how many cells are left. That's okay too. Cover up the last row, cover up the last column, and how many cells are left. They don't care that you show this multiplication. They just need to know the DF. Cover up the last row and the last column. Just remember, you're not covering up the totals. Don't cover up the totals and count 3, 6, 9. That's wrong. Don't cover the totals and count the last rows and count. Beautiful. Okay, that's a DF. It'd just be 4. It'd just be 4. 2, 2. Okay? All right. Pretty much we've done everything. Let's look at this example. For a class project, Abby and Maya want to know the gender of an interview could affect the responses of a survey. The subjects in their experiment were 100 males from their school. Half the males were randomly assigned to be asked, would you vote for a female president? By a female interviewer. The other half of the males were asked the same question by a male interviewer. The table shows the results. State the appropriate null and alternative hypotheses. The gender of the interviewer has no determination on the answer. The gender of the interviewer has no effect on the answer to the question. The answers, depending on the gender of the person asking the question, will be the same. There's a bunch of ways to say that. There are a bunch of ways to say that. We just have to think that there's no difference in the answers. The answers will be the same. The gender of the person asking the question will have no effect on the answer. The gender of the person will have the answer to the question via the gender of the, I guess the gender of that needs to be stated. Hit me, Jeremiah. So as long as you don't allude to the sample, you're okay. True would be a good word. We like to throw that word true in there. Okay? We like to throw that word true in there. Here's what they said. There is no difference in the true distribution. So there's Jeremiah's good on that, right? The true distributions of the response to the question when asked by a male interviewer and when asked by a female interviewer for subjects like these. Y'all kind of remember that too, right? This was random assignment. So subjects like these. So really all we're talking about are males because this was all 100 males. And then we talk about there is a difference. There is a difference. Question? Again, 29 of you cats in here, 28 of you cats, y'all could all have something a little bit different. But no difference, equal, the same. Well, what are we talking about being the same? Well, our question is, does gender of the interviewer have an effect on the answer? That's what they're trying to figure out. Well, we assume that the gender of the interviewer has no effect on it, and it does have an effect on it. Good enough? Show the calculation. Oh, you better show the calculation for this one because they tell me to. I better not have just an answer. Show the calculation for the expected counts of the male yes cell. Male yes. That one right there. Show the calculation for that expected counts. Well, I'm going to go to the total right here. And I'm going to go to the total right there. And I'm going to multiply those two numbers together. Multiply 69 and 50 and divide it by the table total. And that's going to be the expected counts for that cell. Okay? Y'all okay with that? That's a multiple choice question on your next test, I promise you. What is the expected counts for this cell? Show it. Now, if it's multiple choice, of course, you don't need to show anything. Don't round. Don't round. If it has unlimited decimals, then you can round, right? Unlimited decimals, you can round. But don't round to an integer. Here are all the observed counts. Here are all the expected counts. Verify that the conditions are met. Random assignment. of 100 males. What does that mean also with my 10%? Don't check it. Don't check it. All expected counts greater than or equal to 5. There they are. There they are. You have to prove it. You can't just say it. You can't say it. You must prove it. You can't say n times p is greater than 10. You got to prove it. You can't say that n is greater than 30. You got to prove it. N equals 58, greater than 30. You got to prove these things to show that you actually checked the condition. So your calculator will do it all at one time. So they're going to give you this. I know you guys are working a little ahead. They're going to give you the observed counts, just like a table. They're going to be in a table. Okay, they're going to be in a table. If they're in a table, you're not doing a GOF test. If they're in a table, you're not doing a GOF test. They're going to give you the table. All you need to do is write down the expected counts with it. I don't even make a new table. I get so lazy, I don't even make a new table. I put down 34.5. And I'll put down 34.5. Notice that these are the same ratios because this is 50 and that's 50, right? 5.5. So I'll just put it in there and I'll say all expected counts are greater than 5 and I'll say see table. And that saves me from having to make a table, and that saves me from having to write them all down and write everything down again. I just have to write down those expected counts. And your calculator will do them all at one time. I'll show you that. Okay? Any questions about that part of it? So we don't check the 10%. All expected counts have to be greater than 5. This is where some students will mess up and put the observed counts. Don't. You put the expected counts greater than 5. Random assignment. Let's see how they did it. Treatments were randomly assigned. All expected counts are greater than 5. See table for expected counts. We don't check the 10%. You don't have to say it. If you do say it, you're okay. Don't say 10% check. You're getting dinged. You're getting dinged. Earlier, they calculated the test statistic at 4.25. They calculated the test statistic at 4.25. They do that a lot. They tell you the test statistic a lot of times without you having to calculate it. That way you can't mess up. Every single student that takes this test gets the same test statistic, whether you mess up or not in your calculator. Okay? Last test, the milking one, right? If you actually did the test, you didn't get the same p-value. Okay, you just did a lot of extra work though. I got a different p-value than the guys that worked out everything. So what? I got a p-value of this. You did a lot of extra work that you didn't have to do. That's the p-value. Compare the p-value to alpha. That's the chi-squared value. I don't care if it's the right chi-squared value or not. That's what they got. So that's what we're going to use. Find the p-value. Chi-squared CDF. Chi-squared CDF, that's always the lower bound, 4.25. Upper bound is always 99999. And then you got to put the DF. Cover up females. Cover up that. DF is 1. DF is 1. Oh, no, there were 3 answers. I'm sorry. There were 3 answers. So, sorry. 1, 2, 3. 2. 1, 2, 1. So the DF is 2. I'm sorry. Okay, DF is 2. So find that p-value. Your calculator will do all that stuff. DF is 2. Using table C, the p-values between those two, because your table's not going to give you the exact p-value, so you just have to tell it what's between. If you're using your calculator, you'll find the exact p-value of 0.119. They'll accept either one. I think it's easier to use the calculator if you want to use the table, Then you go down to DF of 2, and you go across until you find that 4 point whatever, and you won't find that number, so it's going to be between 2, and you go straight up, and those are the 2 p-values. As usual, technology saves time and gets the arithmetic right. So this is how you're going to do these in your calculator, guys. You're going to put the observed counts in a matrix. So let me show you how to do that, because I don't think we do matrices in any class. So you have to put these in a matrix, because that's the only way to get rows and columns. That's the only way to get rows and columns. GOF, you can only get rows. Can't get columns. You can only get rows. So I'm waiting for this thing to crank up. Matrix is like second, and it's one of those on the left-hand side. You'll see matrix. It depends on which calculator you have. Okay? So here we go. This is the only time I'm going to show this. Second, my matrix is right here. That's my matrix, okay? Bless you. These are the names of them, A, B, C, D, E, F, G, H, I. You can name them however you want. I don't have any matrices. I don't have any. These are just the names of them. So if I do matrix A and I hit enter, there's nothing in matrix A. It's empty. Go to matrix A. There's nothing in there. Okay, whatever. I know there's nothing in there because I can see there's nothing in there. And this goes to math. And I don't have a matrix, so why am I going to math anything? I need to go to edit. Just like stat edit. When you got to put your data in there, you got to do stat edit. When you got to put your data in here, you got to do matrix edit. Enter. This is going to ask you rows and columns. And if you do it wrong, it's okay, because it's going to show you. I don't know if it's a 3x2 or 2x3. Well, type it in there. No, that's not what I have. I have 2 of these and 3 of these. Okay, well, go up and change it. I mean, you can't really mess this up. There's 2 of these and 3 of these. Whatever it is, whatever your dimensions are, just put them in there. What was this one? Was it 3x2 or 2x3? 3x2? I think it was 3x2, right? So 3. Yes, yeah, we don't put the totals in there. Yep, bless you. Yeah, we don't put the totals in there because the totals have nothing to do with it, okay? So we just put the data in there. Put the data in there, okay? Somebody hit me these data real quick so I can get the same as you. 30, 39, 8, 3, 12, 18, just plain old 8. Good enough for that. Now, guys, just like stat edit, it's in there until you delete it. It's in there till you delete it. If I hit quit, it's there. It's there forever until you delete it. Okay? And it doesn't affect anything. You don't have to be in radians. You don't have to be in degrees. Doesn't matter. Not going to affect anything. Notice now when I hit second matrix, though, you can see that matrix A is a 3x2. I have information in a 3x2 matrix. Okay? Now, I'm not going to put my my expected counts in. I'm not going to put my expected counts in. Those are my observed counts, okay? So quit. It's there forever until you need the next one, okay? Until you need the next one. Stat. Now, tests. Oh, there's one that just says chi-squared test. This is where you have to be kind of careful what you're doing with the calculator. The GOF says GOF. The other one says chi-squared test. That's for homogeneity and independence. They're both the same. So when I hit enter, look what it asked me. Observed, matrix A. Matrix A. If it's not in matrix A, you need to change it to matrix B. Or if you put it in matrix C, you got to change that to C. How do you do that? I don't know. You'll figure it out. I really don't know. That's why I put everything in A. Notice it says expected in B. Did I put anything in B? No. It's okay. It's going to make a B. It's going to do it for me. It's going to make a B. I did not know this until about year 4. We put our expected counts in matrix B every year. Calculate. It's going to give me 3 things. It's going to give me the chi-squared value, it's going to give me the p-value, and it's going to give me df. And that's what we need. We need the chi-squared, we need the p, and we need the df. So it does all the work for you. It does not show me the contributions. It doesn't show me the contributions, okay? Because those are in lists. It doesn't show me the contributions. But do notice this. When I hit quit or get out of this or clear it all out and I forget everything I was supposed to do, if I go to matrices, look at B. There's a B. It's a 3x2. And if I go down, I'm not going to go to edit. Don't go to edit. I mean, you can, but don't. Just go down to 2 and hit enter. Look, matrix B. What is matrix B? Well, heck, I don't know. There it is. Those are the expected counts. Those are the expected counts. So it lists all the expected counts for you without having to do them individually. But you have to list those, right? Because that's one of my conditions. One of my conditions is all expected counts are greater than 5. You got to list those to prove that they're all greater than or equal to 5. That's close, but it's greater than or equal to 5. Question about the calculator on that. It's all in matrices. Don't try to do a list. Don't try to do a matrices for a GOF. It will mess you up. So if it's a GOF, you have to use lists. If it's a matrices, if it's a independence or homogeneity, you've got to use the matrix. Bo?
So let's say like you use this and then you write down like whatever on the table. You don't have to like write expected counts for the total, right?
Right. Right. You don't know the totals helps you find the expected count. So there are no. You just have to write down those 2, 4, 6 numbers. Y'all hear what his question was when I'm writing down the expected counts? There's nothing in the totals. These are the 6 or 9 2, 4, 6 numbers I have to put down. And you can make a new matrix if you want to. It's okay. Again, just don't. You got to list them. You got to list them. I'm just trying to speed up the process a little bit. Most of the time they give you enough room on the table for you to be able to write it in there. Now, do remember this. You guys are going to get a computer. And your questions are going to be on a piece of paper. And my guess is it will not have a 1 on the piece of paper. So you're going to have to make a matrix. I just thought about that. You're going to have a blank piece of paper, so you're going to have to make a matrix. You won't be able to fill in their matrix because their matrix will not be on your paper. Okay, expected counts. Now, do know this too. If I make a new one, and I go to matrix A, okay, edit. If I make a new A, you don't have to do anything with B. When I do the test, it's going to overwrite it and make a new B itself. So you don't have to worry about deleting B. You don't have to worry anything about B. If I do a new one and it's a 6x6 or whatever, and I do the test, it's going to make a 6x6 here. It's going to overwrite it. So you don't have to worry about B ever changing. Okay? Any question about the calculator on that? Get good at it. Boom. Slideshow. Here we go. Okay. There's the chi-squared test. Here's the chi-squared value. There's the p-value. There's the df. We're good. Beautiful. There's matrix B. Those are the expected counts. They'll show you the decimals. Okay, they won't show you a lot of decimals, but you don't have to show it. You just show whatever they got. Show whatever they got. You can use your calculator to carry out the mechanics of a statistics test. There is risk, right? This is the exact same slide I gave you guys on Monday. Be careful. I like to show 1 observed, 1 expected, squared over the expected, plus I like to put another one, plus ... I like to put 2 just to make sure that that guy, whoever's grading, that person, whoever's grading, knows I know what I'm talking about. And then I tell them what the test statistic is. I tell them what the degrees of freedom are. And I tell them what the p-value is. Because my calculator tells me those things. Why not just tell them those things? You should name it. If you're not sure of the name, don't. If you're not sure of the name, don't, because you will get dinged if you name it wrong. If you don't name it, I'll probably count you wrong. Two-way chi-squared test. That's better than nothing. If it's a two-way table. If you see the table, though, guys, it's either independence or homogeneity. And I'm going to give you a big hint on how you know which one it is. Different countries feel about the importance of speaking the national language. Separate random samples. Homogeneity. I got more than one sample. Of Australia, United Kingdom, and the United States were asked many questions. One of the questions is, some people say that the following things are important for being truly. Others say it's not important. How important do you think it is to be able to speak English? The two-way table summarizes the response to this question. Do these data provide convincing evidence? I got to do the full-blown write-up. Full-blown write-up. I got to talk about the conditions. I got to do some calculations. I got to do a conclusion, and I got to have a ho and a ha. Anytime I talk about convincing evidence, those are the four things you better have. And then there's my ho and my ha, right? That's the question. You guys, the other ones that I used didn't give me the great type of AP type question. Do these data provide convincing evidence that the distribution's opinions of speaking English differ for residents of boom, 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 boom? There's my ho and my ha. There is no difference in the distributions, in the true distributions. Let's go back that. In the true distributions of opinion. There's my ho. Ha. There is a difference. There is a difference. There is a, in the true distributions of opinions. Okay? So there's my ho and my ha. What we have, this was independent random samples. So then we need to mention this, guys. We need to mention that 1,000 is less than 10%. 1460 is less than 10%. 1003 is less than 10% of all. You need to list all three of those because they're independent random samples. We need to talk about it being less than 10%. All expected counts are greater than 5. See table. Don't see this table. Those are observed counts. Those are observed counts. And I'm not going to do that until the end because my calculator is going to do all those for me anyway. Question about all that stuff. The hardest thing about these, I think, is the ho and the ha. Because everything else is the same. Everything else is the same. And I'm going to get my ho and my ha from my question. And then I don't have to worry about it. So I say the hardest part's the ho and ha. The hardest part's naming the test. The hardest part's naming the test. But if they have independent random samples, it has to be a test for homogeneity. Clicky, click, click. Test it all. Random, 10%. Notice that each one of them has to be 10%. Less than 10%. All expected counts are greater than 5. See table. And I didn't put the table. Make sure we write them all down. You got to write them all down. Again, looky here. There is no difference in the true distributions of opinion. I get it right from their question, guys. Right from their question. There is a difference right from their question. And I'm not going to write it down twice. I'm going to write down true, and I'm going to write down one of them, and then I'm going to squiggle, 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 squiggle. No difference. Any questions about that? Chi-squared. I'm going to do one of them. I like to do two of them. Just to make sure that tell that grader I know what I'm doing. Plus, dot, 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 dot. And then I'm going to put the chi-squared test statistic. That's a pretty big one, 68. Chi-squared values can get huge. They can get really, really big. Be careful with this one. Be careful with this one. It's going to give you a p-value of 1 point something. Maybe 3 point something times 10 to the negative whatever. Just be careful. Okay? Because the p-value is less than alpha, we reject ho. there is convincing evidence of a difference. And then I'm going to get it right from the question. There is convincing evidence. Do these data. There is convincing evidence that the distributions, the true distributions of the opinion about speaking differ for those three countries. I went through that without making you guys write all that stuff down. Any questions about it? Anything, anything, anything? Many students lose credit because they don't write down and label the expected counts. It isn't enough to claim that all expected counts are greater than 5. You must provide clear evidence. That will knock you down from E's to P's. If you have already a knock, it's going to knock you from P's to I's. All right, real quick, independence. Independence. This won't take very long at all. There is almost no difference between these two. Almost none. Two variables, one sample. That's going to be your clue for independence. One sample, two variables. One sample, two variables. Here's my biggest hint. Here's my biggest hint. Let me do this for you. This, I think, is the biggest hint, and this helps students more than anything else. Okay. If I am comparing or trying to see a difference in just the rows or just the columns, just the rows or just the columns, that's homogeneity. If it's just the rows or just the columns, it's homogeneity. Let's go back to my example. It wanted to know if there was a difference between the countries. It wanted to know if there was a difference between the countries. All I'm comparing about is that. That's homogeneity. Okay? Independence will compare the two rows and columns. Independence will compare both. Is there a difference between that and that? That will be independence. So you look at they're both going to have tables. They're both going to have tables. You're going to look at, what am I comparing? Am I comparing just the rows or just the columns? I think I said that backwards. Or am I comparing the rows and columns? If it's rows and columns, it's independence. If it's just one of them, it's homogeneity. The conditions, watch, same, cute. Formula, guess what? Same. Expected counts, same. DF, same. Hypotheses, really, really close to the same. See, twins, anybody see that movie, you know? Yeah. They were twins, but they weren't twins. Yeah. Hypotheses are really, really, really close to the same, okay? You assume that they're independent. You assume that they're independent. Independent means, be careful of this, a lot of students mess this up. Independence means that there is no association. Association. That's what independence means. They're not associated. If they're dependent, then they are associated. And so some students don't use independent. Some of them say there's no association between blank and blank. Or blank and blank are independent of each other. However you want to say it. Okay? But no association means they're independent. If there is an association, it must be a dependent on something. So a lot of students get that confused. No association is independent. No association is independent. The two variables are not related. They're not related. There's no association. They're not related. They're independent. Any one of those three will do. And again, I'm going to get it from their question. I'm going to get it from their question. This is just what you have to know. You have to know this is what I have to assume. Whatever their question says is what I'm going to put here, but you have to know they're independent or not related or no association. And then the high is they are dependent, or that they have an association, or that they are related. Again, just depends on what their question is. I don't have to decide on one of these three. I'm going to get that from the question. You have to know independent, not related, no association, which is a little bit different because we're always used to talking about how they're equal. And if they're equal, you have to translate that into no association. If they're not equal, then that must mean that there's something affecting it. And so that takes a little bit for us to really dig down into our brains a little bit harder. Okay? Question. Good? Are people prone to sudden anger more likely to develop heart disease? An observational study followed a random sample of 74 people with normal blood pressure for 4 years. Each person took some type of scale test. Researchers also recorded whether they developed coronary heart disease. There's the table. They're trying to see if there's an association between heart disease and anger level. It's independent. That's a test for independence. It's not homogeneity because I'm comparing two variables. I'm comparing two different variables. What do we have to assume? There's no association between those two. And the high is there is. And then everything else is exactly the same. Random sample or random assignment, 10%, all expected counts greater than 5. We put this in a matrix. We do matrix A, or my observed counts. Matrix B will automatically get produced by doing my expected counts. We write down 153 minus whatever squared over whatever plus 110 minus whatever over whatever plus ... Calculator gives me the chi-squared value. Calculator gives me the p-value. Calculator gives me the df. You write down what alpha is, and then you tell me your conclusion. Tell me your conclusion. You should write down this is a chi-squared test for independence somewhere. Yellowstone National Park, each of the 1526 visitors in the sample was asked 2 questions. We actually did this in chapter 1. Do you belong to an environmental club? What is your experience with snowmobiles? There's the two-way table. Do these data provide convincing evidence? I got to do the full-blown deal. Of an association between environmental club and snowmobile experience. This is a test, chi-squared test for independence, because I'm comparing 2 different variables. And then assume there is no association between environmental club status and environmental. There's my ho, and ha, there is. Y'all okay with all that stuff? Again, see how I'm getting it from the question. See how I'm getting it from the question. Random 10% large counts. All expected counts are greater than 5. Make sure you list them. There is no association. I'm getting it from the question. There is an association. I'm going to put down chi-squared test for independence. That's probably the most missed type, is not naming what you're doing. Chi-squared, I'm going to put down one of them. I'm going to put down another one. I'm going to put down ... I'm going to put the chi-squared value. Holy cow, 116. Huge. My guess is p-value is really, really small. There it is, 4.82 times 10 to the negative 26. Please don't put down the p-value is 4.82. Please. Please. DF is 2. Your calculator gives you all that stuff. Because P is so darn small, we got to reject. There is an association. This happens a lot in this chapter. Okay, when the p-value is really, really small, the calculator will report it using scientific notation. Remember, p-values are the probabilities and must be between 0 and 1. If your calculator reports a p-value and a number that appears greater than 1, look to the right and you'll see that it's in scientific notation. If you claim that the p-value is 4.82, you're going to lose more than credit. I'm going to drop A's to B's and B's to C's and C's to D's and D's to F's. And if you're already at F, I'm going to drop you further. Because there's no way to tell me that the p-value is bigger than 1. The best way to distinguish between those two is how is the data produced. I still think the best way is to determine what you're comparing. You're just comparing one side or both sides. If the data comes from 2 or more independent random samples, it's homogeneity. If the data comes from a single sample but 2 variables, it's independence. Also ways of helping you. Looky here. Looky here. A beef distributor wishes to determine whether there is a relationship between geographic region and cut of meat. The observed counts are below. Is there sufficient evidence to suggest that geographic region and beef preference are associated? GOF, independence, homogeneity. Y'all good? I'm comparing cut area independence. That has to be independence. The person right here is they came from one sample. They came from one sample. I went to one person. Where do you live? What do you like? You got 2 answers from one person. That has to be independence. Does your zodiac sign determine how successful you're going to be? Fortune magazine collected zodiac signs of 256 heads of the largest 400 companies. Is there sufficient evidence to claim that successful people are more likely to be born under some signs? One sample, one answer. That's golf. That's a golf test. That's a golf test. One sample, one answer. Here I have a table. It's either independence or homogeneity. The following data is on drinking behavior for independent, chosen random samples. Homogeneity. Done. Independent random samples. You got more than one sample. Does there appear to be a gender difference? All I'm comparing is gender difference. I'm not comparing gender difference with drinking. I'm comparing is there a difference in genders. Is there a gender difference with respect to drinking behavior? All right, I hope you can state the appropriate hypotheses and compute the expected counts, as well as the test statistic. I hope that you can check and state the conditions, random 10%, large counts. I hope that you can calculate the DF for a two-way table. I hope that you can perform the chi-squared test for homogeneity, and I hope you can perform a chi-squared test for independence. I hope you can choose the appropriate chi-squared test. This is probably the hardest. That is one of the hardest. Just recognize, where did the data come from?